So in the last video, I described how to interpret three-dimensional graphs. And I have another three-dimensional graph here. It's a very bumpy guy. And this happens to be the graph of the function f of xy is equal to cosine of x multiplied by the sine of y. And I could also say that this graph represents z is equal to that whole value, because we think about the output of the function as the z coordinate of each point. And what I want to do here is describe how you can interpret the relationship between this graph and these functions that you know by taking slices of it. So for example, let's say that we took a slice with this plane here. And what this plane here is...
3JS gives you a bunch of ways to form rotation matrices. Here's what one of them looks like, a rotation around the z-axis. The Greek letter theta is the angle of rotation. The cosine and sine of this angle are used to form a somewhat symmetric piece of the matrix here. The rest of the matrix is left alone. By leaving these values in the third row 0 and this value here being 1, this has the effect of leaving the z-coordinate untouched. This makes sense since when you rotate around the z-axis, the z-values shouldn't change. Here's a real rotation matrix around the z-axis for a rotation angle of 53.1 degrees. As an example, the coordinate 1, 0, 0 transforms to the coordinate 0.6, 0.8, 0. The coordinate is rotated counterclockwise around the origin. One way to look at things is that you're rotating a point from one location to another. Another way to look at it is that you're changing the frame of reference. The rotation transform can also be thought of taking our original point and looking it up to see what value it has on these two new axes. For example, on our new x-axis, the point's coordinate is 0.6. On our new y-axis, the point's coordinate is 0.8. On the left, we're rotating the coordinate with respect to the axes. On the right, we're rotating the axes and then seeing where the coordinate lies with respect to these axes. Either interpretation is correct, and both have their strengths. If we rotate the first interpretation so that the x and y axes are aligned with the second, we see that the transformed point is in the same orientation to the axes in both cases. This second interpretation is the one that helped me understand how a dot product is rotating a point. In an earlier lesson, we talked about how the dot product between two normalized vectors gives us the cosine of the angle between them. Rotation is a similar use of the dot product. We use the cosine of the rotation angle to give us two new axes, both of which are normalized. That is, their lengths are both 1. The dot product between our test point's coordinates and each rotation axis